Yes. Okay, so this is a hemshech. I stopped in the middle because it was 15 minutes. It's a hemshech to the previous tape. This is again representing the horizon and the right ascension declination. The two coordinates here. The red one represents this is celestial equator. This is the declination of 10. The stars are 10 degrees above the celestial equator, and this is 10 below. This is the north celestial pole, south celestial pole. And the black lines is the local horizon in Eretz Yisrael. This is the horizon, this is 10 above the horizon, and so on. So, the previous tape, we explained a very interesting point. We explained that there is, I'll say it now in a different version. Everything you understand in a few ways, you understand it better. So, we'll say it like this. Given there's a certain point of the celestial equator right here now. I want to paint it. We'll take this, color it. Okay. Let's assume this is 10. 10 is right now 10. It can be anything. It can be 10, 13, 14, 15. But I'll make up that right now in Eretz Yisrael, the point of 10 degrees of the celestial equator is on the horizon. It's about to set. Obviously, this is 20 degrees. It's going to set in 40 minutes. So, somebody can ask the question, how long will it take for a star that has a right ascension of 40 to set? So you can say, look, this is 10, 20, 30, 40. 40 is here. So it's 30 degrees, 30 apart from 10. So 30 times 4 is 120 minutes. That's 2 hours. However, this is not the right answer because you have to also add this is only if that star has a declination of 0. That means it's on the celestial equator. If you have the same thing, the same right ascension, however, so it's right ascension of 40, right? You said this is 10, 20, 30, 40. Right ascension of 40, but a declination of 10, 20. I'll paint this point here. This point here, this orange point, is a declination of 20. For him, even though he has the same right ascension, he also has a right ascension of 40. Let's see how long it will take for him to set. So you have to go through this area. That's 10, 20, 30. Times. No, I didn't reach the horizon yet. 30, 40, and here I'll paint where it reaches the horizon. So look what's going on here. 10, 20, 30, 40. It's even a drop more. It's 40, let's say it's this area here. It's 42, it looks like 42 degrees. So 42 times 4 is 168 minutes. What does that show? It shows that if you go higher up the declination, even though you're dealing with the same right ascension, this is right ascension of 40, this is 40. The higher declination, it takes longer to set. The same, whatever I'm saying now can be also said by the lower declination. Look something here. Look how fast it's going to set. There's only one thing here. So you have a star on this declination. Here, right here sets already. So it's just 40 minutes. The other factor is obviously the right ascension. So if it has a higher right ascension, if it's here or here, it takes longer. So there's two factors that determine the time. If I give you a certain point of the right ascension that's on the horizon right now, and or asking you a different thing, a different star, how long it will take to set, you have to know the right ascension and the declination. These two determine the factor. Now sometimes you can have, I'm not going to show it here because it's confusing, you can have sometimes a lower right ascension. Let's say this is the right ascension only of 20. And then there's a higher right ascension. The lower right ascension will take longer to set because it's such a high declination. You can figure it out yourself. It's hard to, you have to print out this paper and then take a pencil and follow and see how much degrees it is till it sets. And you'll see how long it may take. Even though the right ascension is lower, it's low number. Let's say it's only 20 as opposed to 40 or 50. So this is very important to understand. This is the Yisoida, and I should have said this in the beginning of everything. That's why I'm so marach in this. Now, once you understand this, let us now return to the Rambam. We'll give an introduction and then another picture, and hopefully by the next tape we can finish the introduction. So, we have now the idea that we want to find out how long it takes for the moon to set. We know what point of the ecliptic. Now don't get confused now. This is not this picture here. We're not showing it right now. But we'll try to refresh your memory. We have, besides this whole grid, you have another grid. I cannot show it here because it's so confusing you won't understand anything. There is also an ecliptic. That's the Galgal Amazonas. That's also when a guy has an horizon, he has an ecliptic that we had already before. It can be inclined up to 80 degrees towards the horizon or 30 degrees. We explained that. So besides this whole coordinate system of right ascension and declination, there is also a coordinate system of, we'll give it a name. It's called Kave Oirech and Roichav. In English it's going to be called longitude and latitude. Now it's not longitude and latitude of Earth. It's longitude and latitude means here longitude of the ecliptic. So that's why we say that Tele goes from 0 to 30 and it has and the latitude is 0 because it's on the ecliptic. Anything that's above the ecliptic is called latitude of 1, 2, 3, 4, 5. If you remember, the moon can have a latitude up to 5 degrees. That's the most you can go above the ecliptic. So right now, forget about right ascension declination. Just imagine, go back to your old ecliptic coordinates. That's latitude and longitude. Okay. The Kadmonim dealt much more with this system, the system of longitude and latitude. Today, most people, the books, everything deals with this. It's more practical to deal with right ascension declination. Anyway, let us see now. The thing was like this. We need to know. We know what point of the ecliptic is on the horizon. Why? Because that's sunset. Let's say we know the sun is by Shoyer. So when you see the moon, Rambam says it's a half hour after sunset. So roughly speaking, it means when the point of, let's see, the sun is by Shoyer. So when 30 degrees of the ecliptic is on the horizon, that's when we are interested to see how long it will take for the moon to set. So let's assume the moon is also exactly on the ecliptic. The sun is Shoyer and the moon is 15 degrees in Shoyer. 15 degrees in Shoyer. So we have to know how long will it take for that point to set. How long? So we showed, actually we didn't show yet the chart. Maybe we showed it already once. Show it again soon. It's a special chart the Kadmonim had, and we have also a nice chart for that shows from any point of the ecliptic to the next point of the ecliptic how long it takes to set. It's a complicated matter because you have to use special formulas for that, but there is a way. We did it before. We showed a certain triangle, spherical triangle. We have these three things that arise in the ecliptic, and then we can, for some way, we can calculate any given point of the ecliptic from point A to point B, how long it takes to set. We also spoke that the area of Teleh on both sides, let's say from Teleh to Shoyer or from Dogim to Teleh, that takes the longest to set. That area, that 30 degrees. And then from Iznayim, it's the other way around. It sets very fast. We're going to show probably soon, maybe the next tape or the two tapes from now, the chart that shows the Shekiyas Hamashve L'umas Shekiyas Hamilke. It's taking these two things to show how each degrees of the ecliptic sets versus the degrees of the celestial equator. So, l'chayra, we're very good. We know from this information how long it takes. 15 degrees. We take a look at the chart, and the Rambam had that chart. And we know how long it takes from, let's say the sun is by Shoyer, the moon is by 15 degrees of Shoyer, that's 45, and the sun is by 30. We can look at the chart to see how many minutes it takes. Because that's very important, because that shows the amount of minutes it takes, that shows if the moon is going to be visible, or it's going to set too fast, it's not going to be dark enough. So this is a very important factor to know how many minutes is from sunset to moonset. So this should be the end of the Rambam. However, since we know that the moon is not on the ecliptic itself, this is the punchline of this whole shiur, it has a certain roichav tzfoini, or roichav droimi. So we need to do some kind of fixing here, of adjustment. Now, what is the tactic that the Rambam uses? What kind of tactic of adjustment? What he does is, he takes the point. Let's assume the moon is now not exactly on the ecliptic. Instead of saying it's 45, that's 15 degrees in Shoyer, 45.0, it's 45.5. So we have a new chart that tells us which 45.5. I'll show soon the picture for that in maybe the next tape, how we figure that out. But let's get the concept first. Which point on the ecliptic itself has the same right ascension as 45.5? In other words, we have 45.0 and 45.5. But 45.0 is not the same right ascension as 45.5. And we want to take this point 45.5 and find a point on the ecliptic itself that has the same right ascension as the point 45.5. It might be 43, 42, or 47. We'll see the chart soon, and you'll understand better what's flying here. If you don't understand yet what I'm talking about, don't be worried. But because the next shiur I'll give a nice diagram, you'll have what's happening. But again, I just want to repeat before I finish this tape. The concept is, we are looking on the ecliptic itself, a point that has exactly the same right ascension as 45.5. Why? Because we only have a chart that tells us